In this video, I wanted to talk about a little bit of limits and L'Hopital's rule. And to be honest, I don't want to solve many of these problems. I'll solve a few of them, but I don't want to solve many of them. I just want to kind of talk about the ideas behind a lot of them. So this first one, if you plugged in 1, you would get 0 over 0, and you would use L'Hopital's rule. And maybe I'll just make a little note like L'Hopital like that. Okay, and maybe that'll be my shorthand. And you could do L'Hopital's rule. Of course, you'd have 3x squared over 2x. You'd plug in 1 again, and you'd get a limit of 3 halves. Okay, let's go over. If you plug in 2 to the 4th minus 16 over 2 to the 5th minus 32, again, you would just use L'Hopital's rule because it is an indeterminate form of 0 over 0. This next one. 1 plus the natural log of 1 is 0 over 5x, or 5 times 0. So it is also a L'Hopital's rule problem. And if you found the derivative, if I can just remind you, it would be 1 over 1 plus 3x times 3. Derivative down here would be 5. It will now work. Okay, it'd be 1 over 1 times 3 divided by 5, so it'd be 3/5. If you found that. This one, this number 4, if you plug in infinity, you're going to get infinity over infinity. That is one of the cases where we can use L'Hopital's rule, right? Infinity over infinity. If you found the derivatives, and just follow my chain of thought, the top will always be e to the x. The bottom would be 3x squared. Plug in infinity, you're still going to get infinity over infinity. Do it again. E to the x over 6x. Still infinity over infinity when you evaluate the limit. Finally, e to the x over 6. That is infinity over 6. The limit is infinity. So I'll put the limit there. L'Hopital's rule, you can do it multiple times. Just remember that infinity over infinity is one of our indeterminate forms. Next, x approaches 0. Well, if you plug in 0, you're going to get 0 over 0, so you can use L'Hopital here. The big thing to notice is to find the derivative of the top, you would need product rule. Okay, but L'Hopital will work. Next, the limit as x approaches 0. This is actually the definition of a derivative, but you could definitely use L'Hopital's rule here, remembering that a is constant. So the derivative of it would be 0. So you'd end up with cosine of a, or the derivative when you do L'Hopital's rule would be negative sine of a plus x over 1, because this whole term, the derivative of this constant, would be 0. Okay. Going to infinity on number 7, you get infinity over infinity. So this is a L'Hopital's rule problem. I'm just going to write infinity over infinity. So you'd use L'Hopital. Okay. This is just to kind of remind us of why we got to use it. So if you found the derivative, you'd have 1 over x over 1. And now you go to infinity. Well, 1 over infinity approaches 0. Similar thing would happen here in number 8, but we would maybe have to do a little bit more algebra in that the derivative when we did it would be 1 over x and 1 over 2 square roots of x, which we could rewrite as 2 square roots of x over x. And we could do a little work here. Of course, 2 square roots of x over x is the same as 2 square roots of x. Going to infinity, that's 0. Okay, let me just say that again. So you can use L'Hopital here. Almost all of these you can, because you're going to get infinity over infinity. So I found the derivative, dividing by a fraction, same as multiplying by the reciprocal, so I did that. Square root of x divided by x is square root of x in the denominator. Then I plugged in infinity over. Again, I got 2 over the square root of infinity. Okay. So this one is kind of a generalization of that rule. And of course, if you're going to infinity, you can use L'Hopital's rule, where p is some constant. So you're going to get 1 over x divided by p times x to the p minus 1. And you can do some algebra here, and you will see that it is, in fact, going to be 0. Okay. Number 10, not a bad one for L'Hopital's rule. It's going to get 0 over 0. You could handle that. This one, same thing. L'Hopital's rule would work on that one, as well as this one. Okay, and you just find the derivative. Remember your chain rule in both of these. I'm just going to make a note to remember chain rule. Number 13, remembering it's x approaches a, so remember that a is a number. So the derivative of it would be 0. So if we did L'Hopital's rule, we'd have m times x to the m minus 1 and n times x to the n minus 1, because the derivative of these two things here would be 0. Okay. This one, as we put in 0, we get 1 minus 1 over 0, so L'Hopital's rule. And really, I just want to remind you in this case that the derivative of 2 to the x, if we did L'Hopital's rule, and I should notationally, because I have room down here, let me actually put the correct notation. You should rewrite the limit statement that x approaches 0. The derivative of 2 to the x is 2 to the x times the natural log of 2. Then the derivative of 1, of course, is nothing, and the derivative of x is 1. So now you plug in 0, and you end up with just the natural log of 2 as your limit. Okay. And finally here, in this last one, you could use L'Hopital's rule. If you plug in 0, you get 1 minus 1 over 0. Just remember to use your product rule when you find the derivative of the bottom. Now again, I whipped through this in a hurry. I didn't want to solve all of these problems, but a couple things I just want you to be careful of. L'Hopital's rule is great for finding limits of indeterminate forms. You should always start by plugging in the value, substituting in, like in this first one, substituting in 1. Make sure you do get 0 over 0, or like number 4, infinity over infinity. Then you can use L'Hopital's rule. You can continue to use L'Hopital's rule as long as you're in an indeterminate form. For example, if you, in this one, we do it once, in this one we did it once, we got e to the x over 3x squared. That was still indeterminate. It was still infinity over infinity. So we did it again. We got e to the x over 6x. It was still indeterminate, so we did it again. The minute you bounce out of an indeterminate form, you can't use L'Hopital's rule anymore. It has to be one of the forms we've talked about. Remember that you're not doing quotient rule, but you have to find the derivative of the top and bottom separately. But remember your rules when you're doing the derivative of the top. Like here we needed product rule. Down here we would need chain rule. Okay, here we would need chain rule. Here we would need product rule. So remember those. Okay. Remember that after you do L'Hopital's rule, it might be helpful to do some algebra. For example, here we had 1 over x and 1 over 2 square roots of x. If we were going to infinity, we'd end up with 0 over 0, and it would still be indeterminate. We could keep going, but we did a little algebra, simplified it, and we got an answer. And we didn't need to keep going. So if you get something, after L'Hopital's rule, if you get something that you can algebraically manipulate, you might want to play with it a little bit. Okay. So remember, look for indeterminate forms to do L'Hopital's rule. 0 over 0 and infinity over infinity are the most common ones. And look for your derivatives. Make sure you're using the correct rules, and make sure if you get a new after you do the derivative, after you do L'Hopital's rule, maybe do a little bit of algebra. The one last thing I want to mention is right here. This is the correct notation for L'Hopital's rule. And I didn't do it up top because I didn't have room. But by rights, you should rewrite your limit statement. You should say, well, I'm still doing the limit as x approaches 0 of the derivative of the top over derivative of the bottom, because that's what L'Hopital's rule says. It says the limit, as long as you're in an indeterminate form, the limit as x approaches something of a function is equal to the limit of the derivative of the top, derivative of the bottom. But you should, by rights, rewrite the limit statement.